discussion of logarithms, and we'll pass back through the introduction material that I closed the last session with. And we will be talking about properties of logarithms today and their graphs. Okay, now based on the introductory remarks in the last session, if somebody came up to you and said, "What is a logarithm?" what would you tell them? Say, "Go see Robert."
Talk to somebody besides me.
Yeah. Anybody have an idea? What would you say if somebody came up and Max?
A number to the power of x.
That's getting in the ballpark, but not quite right. Anybody else want to offer an idea?
Is it the opposite of an exponential function?
Well, we don't call it opposite.
Inverse.
We call it an inverse. Okay, so that's important for you to remember. We've learned how to form inverses, and how do you form inverses? How do you form an inverse of anything?
X and Y.
You interchange the inputs and outputs. In other words, in algebra, typically with x and y for your input and outputs, you reverse those, and then you solve for y. So if you have an exponential, a logarithm could be thought of as the inverse of an exponential. Is an inverse, and it's actually a function. It's an inverse function. Logarithm is an inverse function of an exponential.
And the exponential doesn't have to be a function.
Well, hold it. Think about what we've talked about on exponentials. Think about their graphs. Think about exponentials graphs. Not polynomials, but exponentials. Exponentials look like either a growth exponential, that's called a growth exponential, or a decay exponential. They don't come back up, they go down towards an asymptote. That would be a decay exponential, falling as you move through the domain. A growth exponential would be growing as you move through the domain. So if you take one of those, either one of those, and notice either one passes a horizontal line test. Each have a domain and a range. If you form the inverse, since these pass a horizontal line test, their inverse would then pass a vertical line test, which means that that inverse will be a function. So here's the idea related to this sort of way of explaining to someone what a logarithm is. If you start with an exponential, say like this, then you interchange your x and your y, and you're going to get a graph that's going to look like this. So here's the exponential, and here's the logarithm. And they will have symmetry around the y equals x line because you're forming the inverse. As I said a moment ago, this passes a horizontal line test. We call that 1-to-1, 1-to-1, passing a horizontal line test. Then the inverse of it passes a vertical line test. Another thing is the domain on the exponential becomes the range on the logarithm. So the domain here becomes the range over here, and the range on the exponential becomes the domain of the logarithm. It's that simple. You just need to remember it. And these little pictures, this pair of pictures right here gives you this thinking. It sort of graphically explains this thinking. And this is a strange word, as I mentioned in the last session. It's a strange word made up of derivatives, I believe, from Latin and Greek. Logo or rhythmos or something like that. I don't speak those languages. But the people that invented these hundreds of years ago did. There is another way that you could explain to somebody what a logarithm is. You could say that the logarithm is just an exponent. Let's go over here. A logarithm is just an exponent. Now, what does that mean? So here's what we did. If we started, give me a base. Give me a base for an exponential. 5. Okay, so if we have an exponential expression, like Todd suggested, a base 5 exponential, this thing graphically would grow as a multiple of 5, and it would be pretty steep as it moves out to the right. And it has what y-intercept here? 0, 1, Jerome, right. 0, 1. When you come over to 1, how tall is it? 5. Everybody agree with what Jerome's suggesting? Okay, you're at 5. When you go over to 2, you're up to 5 times 5, or 5 squared. So as I've said repeatedly, an exponential function grows as you move through the domain. It grows as a multiple of the base. It grows as a multiple of the base. Okay, now, how do you form a logarithm? We just talked about it. How do you form a logarithm?
Switch the y and the x.
You interchange the x and the y, and we did this in last session. So we have 5 raised to the y power equals x. So look up here. A logarithm is just an exponent. A logarithm is just an exponent. Well, the mathematicians decided to write this as y equals the logarithm. In other words, you can think of this as an exponent. Base 5, you have to put a little subscript there, of x. So these two expressions right here and here are the same. These expressions are the same. In other words, the exponent, when you see a logarithm, folks, you can substitute mentally or say it out loud if you wish. You can say exponent. What's the exponent of 5 that gives you x? Look at this right here. What's the exponent of 5 that gives you x? Okay? So that's a handy thing for you to help you. The sketch of this relationship you see right here is going to be what I just said on the previous board. It's going to look like this, going through what important point? 1, 0. And what would be another very important point?
5.
If you go out to the base's value, out here to 5, this thing's going to be up at a height of 1. Just like up here, if you went over in the domain to an input of 1, you're going to have an output of 5. So that 0.15 becomes 5, 1. So let's practice. Let's practice a couple logarithms, and why don't we stick with what Todd had suggested, base 5. So here's a question. Log base 5 of 1. What's that equal to? So what you want to say to yourself is, what's the exponent of 5 that gives you 1? Logarithm is just an exponent. What's the exponent of 5 that gives you 1? Think about it. Jennifer?
0.
0. Perfect. So log base 5 of 1 equals 0. What's the exponent of 5 that gives you 1? 5 to the 0 gives you 1. What would be another way of writing this first question mark right here, this equation right here, and I'll keep the symbol for question mark in here. What would be another way of writing this? 5 to the unknown power, the question mark, equals 1. And Jennifer answered that, has to be a 0. This statement and this statement are identical. These two statements are identical. And that's the same thing that is being stated over here in general. 5 to the y equals x, or y equals log base 5 of x. So there's some new vocabulary here. One new word is all. And the fact that you're already familiar with domain and range, and the key to understanding this is having an understanding of the exponentials. And if you have an understanding of the exponentials, all you do is interchange the inputs and outputs and then solve this thing for y. Y is equal to the log base 5 of x. Let's try a couple more. Let's stick with this base 5 for a second. Oh, one more question. Where is this information on this picture? Look right here, folks. This is an equation, isn't it? This is a function. It's passes a vertical line test. And here's the equation for it. Okay. Here's the equation for this graph. Where is this information right here on this picture? What's the input? What's the input? 1. So you go over to 1, and the output value is 0. This is your x-intercept of this logarithm. This is the x-intercept of the logarithm. These take some practice. Just like everything, as you learn something new, it takes repeated practice to become proficient with it. Here's another question. Log base 5 of 5 equals what? Here's what I want you to think of mentally. What do you think the answer is, Mac? 1. 1. Okay, in other words, what's the exponent? I'm trying to get you in the habit. When you see the word logarithm, think exponent. What's the exponent of 5 that gives you 5? As Max said, it's 1. Okay? The answer here, log base 5 of 5 is 1. What if it was a different logarithm? What if it was a log base 10? Log base 10 of 10 would be 1. Log base 2 of 2 would be 1. And where are you on the graph of the logarithm? Where are you on the graph to illustrate that information? Log base 5 of 5 is 1. The input is 5. The output is 1. That would be this location right here, wouldn't it? Your input is 5, and your output is 1. So for other base logarithms, like 10, like 2, etc., you have to go over in the domain to the basis value. You have to go over in the domain to the basis value to find a height of 1. So if I was dealing with a log base 10, which is called a common logarithm, and I'll give you more detail on that in a second, if I went out here to 10, I would be up at this same height 1 if I was on a logarithm base 10 graph. This would be a log base 10 of x graph right there, and that would be up at 1. So again, it'd be out here at 10, I'd be up at a value of 1. Okay. If you can keep those things in your head, these things will always be 1. What I mentioned in words a moment ago is log base 10 of 10 is 1. Log base 2 of 2 is 1. The equivalent statements shown here is that the exponent here is 1, isn't it? So you see these logs here? The exponent is 1. the exponent is 1, the exponent is 1. The base is shown right here as a subscript. So this says 5 to the 1 equals 5. 10 to the 1, the exponent is 1. 10 to the 1 is 10. 2 to the 1 is 2. And those are just points on the graph. You have to go out to the basis value to be up at a height of 1. So I'm trying to make an algebraic connection for you and a graphical connection. Let me see you folks do one now. Let's come over to the other board. Log base 10 of 1,000. Log base 10 of 1,000. Sarah? I'll help you. What's the exponent of 10 that gives you 1,000? 3. Good. Okay. Leah, you want to try one? Sure. Okay. Log base E of, making it more exciting, huh?
All right.
E to the 5th.
Would just be 5.
It's 5, right. What's the exponent of E that gives you E to the 5th? Okay. Not too bad, is it? Okay. So, let's see what else we could do. I want to do one more with the base 10. And then I want to draw the graph of the base 10 logarithm. Because this is very important. This one is used a lot. The Richter scale for earthquake intensities is a logarithmic scale. The hearing decibel ratings are logarithmic scales. Go to a really loud rock concert and the sound is up around 120 decibels. You go to a duck game at Thompson Stadium, the sound level is up close to that. Not too far off from what the intensity of a jet engine near, as a plane comes in for landing over you and you're right there near where that plane's coming in, or plane taking off, a jet engine taking off. That sound intensity is up there around 120, 140 decibels. Those are logarithmic scales. pH in your shampoo, pH balanced shampoo, that's a logarithmic scale. pH is the hydrogen ion concentration that exists in something. It's a measure of the acidity or the alkalinity of the substance, the material. You eat a tomato, it's got a little bit of acid taste to it. A lemon, similar, okay? Those have a pH value that is less than 7. They're acidic, okay? What do you clear a plugged drain in your bathroom sink with? Either a plunger is a mechanical way of trying to do it, but you also can put something like Drano in, sodium hydroxide, which is an alkaline type of substance that'll eat the gunk that's in your trap of the sink drain. And has a different pH. It's way above 7. 7 is considered neutral. Okay, we'll talk about those things a little bit later. Earthquake intensity, decibel ratings, and pH kind of things. Okay. Let's do one more base 10 logarithm. Log base 10 of 10,000. Answer, Todd? 4. What's the exponent of 10 that gives you 10,000? 4. Now, what is really interesting about looking at these numbers right up here on the top, the base 10 logarithm, is you should immediately, just like your basic family of graphs that you've already learned, when you see logarithm, you should immediately think of the graph. I would encourage you. And so this is going to be a base 10 logarithm, which means that it comes up off this asymptote, goes through 1, 0. In other words, the log base 10 of 1 is 0. Input is 1, output is 0. And you have to go out how far to be up 1? Good. You have to go out to the base to get, here's the base's value. You have to go out to the base to be up to a value of 1. Now, how far out do you have to go to get up to a height of 2? Here's 1. There's your 1. How far out do you have to go to the right to be up to a value of 2? You have to go out to, Melissa? 100. Let's see, if this is 10, if this distance right here is 10, then 100 is about halfway over to the far wall to just get up to 2, right? And to get up to a height of 3, look up here, to get up to a height of 3, you have to be out to 1,000. 1,000, that's out in the hallway. Okay? And to get out to, up to a height of just 4, I have to be clear out at 10,000. 10,000 is 1,000 times 10. So if I went 1,000 times this distance that way, I'd be clear off out of the building to be up just to a height of 4. So what you can observe from this is that when you see large changes at x, large change in x on logarithms, you usually see a very small change in y. Small change in y. If you take a Richter scale for giving us a rough estimate of the intensity of an earthquake, if you have a Richter scale intensity of 6, that's a pretty good shake. I was in college and high school in Los Angeles, and I was in a couple pretty good ones. And that's pretty unnerving when all the land around you starts moving and the building you're in or whatever starts shaking and things start flying. Okay, earthquake intensity of 6. If you go from an earthquake intensity of 6 to an earthquake intensity of 7, the amount of intensity, the intensity of the earthquake has, the energy that's been released is 10 times as much. 10 times as much energy release. So it's a base 10 logarithmic scale. A magnitude 8, like the severe shakes like that have occurred near 8 up in Alaska and out in the Pacific, that's 100 times a 6. Okay, so logarithmic scales base 10, they change as multiples of 10. Multiples of 10. Okay. So you have to go, this thing really goes out fast and it rises very slowly. Okay, that's important. Let's look at a couple other things and then we'll start doing some practical problems in the time that remains today. Let's look at a logarithmic equation. As you've noticed, every time you master something in math, we give you something new that sort of scrambles your brain a little bit. And then it takes a lot of practice on your part to get good at that new item. And then we give you something else. Okay. So just be aware. Anybody taking chemistry this year right now? Are you playing with logarithms at all yet?
Oh, yeah.
Oh, yeah. For pH and other types of things like that? Yeah. Okay. Okay. Let's look at let's think of a graph for a second. Log base 3 of x. Draw a quick sketch of that. If you're watching the DVD, pause it for a second, draw a quick sketch. And label at least 3 points. Label 3 points on the sketch. Time's up. Okay? So, the graph looks like this. There's one point labeled. Somebody want to give me another point? Max?
3.1.
3, 1, right?
3, 1.
Perfect. And another one, somebody?
9, 2.
9, 2. Great. Sounds like you're listening. That's good. Okay. 9, 2. Okay. Domain? Look at the picture.
0 to infinity.
Not including 0, though. Greater than 0. Right? Range?
Infinity to infinity.
All real numbers, right? Negative infinity to infinity. Good. Everybody okay with this? All right. Try this. On that same sketch, let's draw this. 1/2. 1/2 is in here in front in my writing. It's kind of messy. 1/2 logarithm base 3 of x plus 2. What does the 1/2 do to the graph?
Smush it.
Squashes it, makes it half as tall. The heights, see here are your heights, these values. These are your outputs. Are made half as tall. So here's my little code I like to use. And, careful, this is inside, messing with the input. You're messing with x.
Going left.
Left 2. Go back and think about the circles we did at the very beginning of the course, how if you had an x plus 2 quantity squared in your circle equation, the circle center shift and the whole graph is shifted 2 to the left. So the sketch of this thing then is going to be taken 2 to the left. What happens to this vertical asymptote here? It goes with the shift, doesn't it? It goes with the shift 2 to the left. So you take it 2 to the left, you label it as a vertical asymptote, and then you take your graph and bring it 2 to the left. And if you're taking and multiplying the heights, if you're distorting the thing first by making it half as tall, what's half of 0? Half of 0 is still 0, isn't it? So that point just simply gets shifted 2 to the left. That's important. So minus 1, 0 is your 0 of the new graph. Now I've got a tricky question to ask you. Tricky question. We were out here at 3 and up 1 on the basic logarithm graph, weren't we? Where does that point go to on this new graph? 3, 1 becomes what?
1 and 1/2.
Becomes what?
1 and 1/2.
1.
1.
Got 2.
No, Jennifer, let me go with Jen. You go ahead. What do you think?
It's
What x value?
a half.
A half for the x value?
The x value is 1,
X value is 1
and the y value is a half.
right here.
Yeah.
1 comma 1/2. Does anyone else agree?
Is that right?
Melissa and Leah agree? Okay. So let's check it. If you took this graph and made it, if you made this graph half as tall, there it would be at 3 and 1/2 in height, first of all. And then you take that point and move it 2 to the left. 1, 2, right on. Looking good. Everybody agree with that? So what happens then is this graph is going to have similar character, and it goes out looking like that, doesn't it? And you'd have to go out to what value to be up at 2? Well, actually, I'm sorry, not 2. If you went out here to 7, if I went out here to 7, my scaling's getting off here. If I went out to 7, it would be up at 1, wouldn't it? Sorry for being so messy here. I'm going to redraw this in just a second. So the picture, the final picture here, we would want to fairly neatly draw it. It would be like this, x equals -2. And it would go through this point, and it would go through 1 and 1/2. And then it would go through out at 7, it would be up at 1. And we get a nice looking picture looking like that. And that's the graph of y equals 1/2 log base 3 of x plus 2. How can I check what I just drew? How can I check with what I just drew? I can drop these inputs in and see what I get. Drop the inputs in and see if I get, drop in a -1. If I drop in -1, can I fit it on here? Yes, f of -1, let's see what we get. We get 1/2 of the log base 3, put in a -1 here, of 1, right? And what's log base 3 of 1? What's the exponent of 3 that gives you 1? What's the exponent of 3 that gives you 1? 0. That's a 0 right there. And so we get 0 as a result here. That's this point right here. Let's try putting an input of 1 in. Input of 1. I get log base 3 of 3 with a 1/2 in front. What's the exponent of 3 that gives you 3?
1.
That turns to 1, and we get a value of 1/2. And if I put a 7 in, f of 7, checking this point, 7, 1, I'm checking it. Putting that in, 7 in here makes this 9. 1/2 of log base 3 of 9. The exponent of 3 that gives you 9. I want you to be able to say that as easily as I do. Of course, I've been doing this for years, okay? But that's the objective. What's the exponent of 3 that gives you 9? That's a 2. 2 times 1/2 is 1. Checks, 7, 1. Okay? So what you do is, this is nothing more than transforms that we've learned earlier. If you understand your fundamental graph, you should be able to sketch this thing fairly quickly and answer the questions like what the domain and the range is. What other point would be a good one to plot on this picture?
Y-intercept.
The y-intercept, always. And y-intercepts are usually easy, aren't they? Because we let the input be 0, right? So let's find that y-intercept. And so we're finding f of 0, and so we're going to have the 1/2 of the logarithm base 3 of 2. Now think about this value mentally. What's the exponent of 3 that gives you 2?
2/3.
I have to scratch my head on that one. What's the exponent of 3 that gives you 2? It's got to be smaller than 1, doesn't it?
1/3.
Doesn't it have to be smaller than 1? But it has to be bigger than, what's the exponent of 3 that gives you 2? Has to be bigger than 0, but less than 1. Has to be trapped somewhere in between there. Okay? Now, look at the picture. Look over here at the picture. If you look at the picture, you can see that here's your height of 0 back here. And when you get clear out to +1, you're at a 1/2. So somewhere in between here, we're going to have to be somewhere in between 0 and 1/2 is where that value is going to have to be. Are you ready to tackle doing that? Figuring that out? Not quite. We have to learn a little bit more about logarithms before we can exactly answer this question, precisely answer this question. Okay, so we're kind of left in limbo for a moment. Okay, keep that kind of question in the back of your mind, and what I want to do is go tackle some of the other properties now of logarithms. We've got some properties related to the graphs here. We've got some properties of some examples of how to determine where certain key points are, and we've also seen a little bit with transformations. But let's go look at some of these other properties for a minute. So let me back up for just a second. If somebody came up to you that didn't know anything about logarithms and they ask you, what's a logarithm, what would you say without looking at the earlier boards?
Exponent.
Jerome?
It's an exponent.
It's an exponent. Okay? What would be another way of explaining it?
The inverse of the exponential.
Right, you guys are listening. That's great. It's the inverse of an exponential. Okay. Now, let me give you 3 important properties of logarithms without proof. They're not too hard to prove, but I just don't have time here in the class sessions to prove them. There are 3 properties that we have to memorize, and they're kind of similar to your rules involving exponents that you've learned earlier in algebra. One rule is called the product rule. Then there is a quotient rule. And then there is a power rule. I'm going to do it by example. Give me some base.
7.
Base 2? Okay. So if I have a log base 2 of 8 times 49. No, I don't want 49. And I don't want 8. Okay. Actually, the 8 will be okay. Let's make it 64. The product of, the logarithm base 2 of the product 8 times 64. What the product rule is simply, if you ever see the log of a product, it's equal to the sum of the logs. The log of a product equals the sum of the logs. In other words, this becomes the log base 2 of 8 plus the log base 2 of 64. Now let's answer each of those parts. See in the back row, is that Jada? What's your name?
Yeah.
Jada, yeah. Jada, what's this right here? Log base 2 of 8.
Isn't that what power of 2 gives you 8?
Yes, which would be?
3.
3, right on, perfect. So that turns into a 3. What's the exponent of 2 that gives you 8? Answer 3. Good? And what's your name in the back again?
Kyle.
Kyle. Yeah.
That'd be 6.
6, right on. 2 to the 6th. What's the exponent of 2 that gives you 64? 2 to the 6th is 64. Very nice. So the answer you get for this strange looking thing, which is the logarithm base 2 of whatever that number multiplies up to, that's 480, that's 514 or 512 or something like that. 8 times 64. The log base 2 of that large number is 9. Precisely 9. Example of the product rule. let's keep. Well, yeah, now you have 3 plus 6. So you do each part and then clean it up. 3 plus 6 gives you 9. Okay, let's look at quotient rule. The log, somebody give me a different base. 7. The log of a quotient, in other words, a ratio. The log of a ratio. Let's do this. Let's make this let's keep it simple, 49 and 7. The log of a ratio is equal to the difference in the logs. So this is going to be the log base 7 of 49 minus the log base 7 of 7. The log of a ratio is equal to the difference in the logs. Taylor, what's this first one? Log base 7 of 49.
9.
Careful, what's the exponent?
7.
What's the exponent of 7? What's the exponent of 7 that gives you 49? Exponent of 7 will give you 49. 2. 2. The exponent of 7 that gives you 49 is 2. Over here, Sarah, log base 7 of 7. Exponent of 7 that gives you 7? 1. So we get 2 take away 1 is 1. Can you check that by doing the arithmetic here? The log base 7 goes into 49 7 times. What's the log base 7 of 7? 1. Okay. The important thing by the example, though, is that the log of a ratio equals the difference in the logs. The power rule. This is probably the most important rule. If we have something to the power, we're taking a logarithm of something to a power. Let me have another base besides 7 or 2. 3. Let's use five to the 6th power. Log base 3 of 5 to the 6th. They call the power rule. If you're taking the logarithm of something that has an exponent, the exponent pops out in front of the logarithm. This is 6 times the log base 3 of 5. The exponent comes out in front of the logarithm. Exponent comes out in front of the logarithm. Examples of the 3 rules. Okay. Let me grab a problem or two out of the book. And here's something that starts. Everybody have these 3 rules? They're not hard. You just need some practice with them. Max?
With the product rule, what would happen if one of the integers was negative?
Was negative?
Yeah, would it just work out the same
Well,
way?
think of the graph of the logarithms we've drawn. Can the input be negative? Look at the graphs of the logarithms that we've drawn on the other boards here. Can the input be negative? Only if the graph shifted. But if in the fundamental form of a logarithm, can you take the logarithm of a negative value? No, you cannot. The domain is restricted, which means this stuff in here is restricted to positive values. Otherwise, it doesn't make any sense. Okay, good. So we have these 3 rules. What I'd like us to do is to solve a logarithmic equation, similar to what you might see in homework. So let's say we had a problem like, I'll just take one out of the book, and I've got about 5 minutes left is all. in your book, page 89, or number 89 on page 295, it says the log base 2 of 2x plus 1 equals 3. What's the exponent? What's the exponent?
3.
3. See, a logarithm is an exponent, folks. You've got a logarithm equals 3. The exponent is 3. The base is obvious. Base is 2, isn't it? So the way you solve logarithmic equations, try to remember what I'm going to tell you right now. If you ever see an equation involving logarithms, that's what it's called, a logarithmic equation. Pretty obvious. What you do is you isolate the logarithm on one side, similar to what you did with radical equations. You would take and isolate a radical, and then how would you get rid of the radical? You'd square both sides on a radical equation to solve it. Okay, you do something similar here. You isolate the logarithm, and this problem already is isolated, and then you write this in exponent form. Write in exponent form. Remember I said earlier, there's two ways of writing these things. And so what you do, once you've got the logarithm isolated, you know what the exponent is. Happens to be 3. And the base is 2. So 2 to the 3 is equal to 2x plus 1. So you write the equation in exponent form, which is what this says, and then this takes you back to being a linear equation in one variable, beginning algebra. So this is 8 over here on the right, and so you move that over and you get 7, 2x equals 7, x equals 7 halves. Then you always have to check these. Always check log equations, because what happens, folks, is sometimes with logarithmic equations, when you write them in their exponent form, you've now got a new equation. And it's possible to come up with answers that are called extraneous, which will not work. In this case, this will work. So what you can do is put that back into the problem and check it. If you put 7 halves in there, that becomes 7, doesn't it? 7 plus 1 is 8, so the log base 2 of 8, is that equal to 3? What's the exponent of 2 that gives you 8? Yeah, 3 equals 3. Checks. That simple. Okay. See if I can do one more real quick one. How about this one? 102, same page. E to the minus 2x plus 1 equals 13. This is called a, what kind of equation? Don't say logarithm. That's an exponential equation. Very good. Okay, it's an exponential equation. How do you solve exponential equations? You take the logarithm of both sides. You take the log of both sides. What base would be nice to use?
10.
Well, hold it. Look at this. E. Wouldn't base E be nice to use? So take the logarithm both sides. So if I take log base E of e to the minus 2x plus 1 equals log base E of 13, then the power rule lets the exponent pop out in front. Right? Notice these parentheses. Everybody hear that? Notice these parentheses. That comes out in front, and we have log base E of E equals the log base E of 13. What's log base E of E? What's the exponent of E that gives you E? Answer, 1. And so now, log base E of 13 is just a number. It's the exponent of E that gives you 13. It's just a number. And it's available on your calculator. The symbolism for log base E is abbreviated LN, meaning natural logarithm. So we want the natural log of 13. You can punch it on your calculator, and you're going to get a number a little bigger than 2, less than 3, ln of 13 or natural log of 13, and then you're going to solve this thing for x. So what I would do is I'd kick the 2x to the other side, make it positive, and I'd bring the 13, natural log 13, back to this side, and I'd have 1 minus natural log of 13, and then I'd divide by 2 for the exact answer.
Shouldn't that be -2?
No, imagine taking the negative 2x over to the other side and bring the 13, natural log of 13 back. I always write the thing I'm looking for on the left, though. Imagine that going over to the other side,
Oh, okay, got it.
and 1 here, and bring the 13 natural log back to the left, like this. I just wrote it that way. Okay, I had to run a little quick on this. That's the exact answer. You could then turn your calculator on and punch that and get an approximate answer with your calculator. We will spend, in the next class session, we're going to spend quite a bit of time solving exponential and logarithmic equations in more detail. But do you see how handy it is with an exponential equation to solve them? You take the log of both sides, and the power rule lets that exponent pop down in front. That's the key. Okay, that's it for today.